Right now, beneath North America, part of the continent's ancient foundation is slowly dripping into the Earth's mantle. This isn't a metaphor. Scientists built a detailed picture from hundreds of earthquakes recorded across roughly 6,000 seismic stations. What they found shows that even the deepest roots of continents aren't as eternal as they once seemed. These mantle drips move unimaginably slow, on the order of millions of years, so there is no immediate hazard. But over geologic time, this process can redirect volcanic activity, reshape mineral belts, and alter the stability of continents themselves. To understand why, we first need to look at what continents are resting on. The secret skeleton of continents. Beneath every stable continent lies something far stranger than most people imagine, a hidden skeleton of rock known as a Cratonic root. These are the ancient cores that keep continents steady, and geologists often compare them to the keel of ship. Just as a keel stabilizes a vessel in rough seas, these roots act as deep anchors, holding continental crust in place far above the shifting mantle. They are not shallow features. Most roots extend around 200 kilometers down, and in some regions they reach close to 350 kilometers. That depth places them in a mantle zone where rock slowly flows like taffy, yet Cratons still resist being worn away. The explanation lies in their chemistry. Billions of years ago, high-degree mantle melting stripped them of the unstable minerals that normally weaken rock. What remained was dense, dry, and rigid material that can withstand intense heat and pressure far better than ordinary crust can. Over Earth's history, these features became the foundation of the continents. Roughly 60% of today's continental lithosphere sits on top of Cratons. Their stability makes them among the oldest pieces of our planet. Some date back over 3 billion years, surviving countless cycles of ocean formation and destruction, mountain building, and supercontinents coming together and breaking apart. For a long time, that survival made them appear close to indestructible. People assumed that if a Craton had withstood billions of years of planetary upheaval, it might as well be permanent. And from a human perspective, they've always seemed like the most stable ground to build civilizations on, flat interiors of continents buffered from earthquakes and volcanism by those keels deep below. But permanence in geology is always relative. As tough as Cratons are, they exist in direct contact with the moving mantle beneath them. Over immense spans of time, those forces can strip sections of root away. The same structures that protect continents for eons carry within them the conditions for eventual failure. That's why, when scientists describe a root dripping into the mantle, it marks a profound shift. What looked unshakable is slowly vanishing into Earth's interior. And this raises a deeper puzzle. If even these buried skeletons can decay, then what does that mean for the supposed permanence of continents themselves? When eternal stones die. One of the clearest examples that Cratons can be dismantled comes from Eastern Asia. The North China Craton, once supported by a keel more than 200 kilometers thick, lost much of its lithospheric root during the Mesozoic. Studies of mantle fragments carried out by volcanic eruptions showed that this once rigid layer thinned dramatically from about 200 kilometers down to less than 80. That timing coincides with widespread volcanism across the region and the formation of rich mineral deposits, including major zones of gold. For geologists, this connection turned the case into more than a regional anomaly. It became the central evidence that Cratonic roots are not permanent and that their destruction leaves a lasting imprint at the surface. At first, it was not obvious how such a vast keel could disappear. But one fact quickly ruled out surface explanations. Erosion, rivers, glaciers, or atmosphere cannot bite into crust lying hundreds of kilometers below ground. The process had to come from deep mantle interactions. And in North China, the timing overlaps with one of the most powerful tectonic forces active on the planet at the time, the subduction of the Pacific Plate under East Asia. As that oceanic plate slid downward, it released fluids that weakened rocks above it and fueled hotter, more vigorous mantle motion beneath the Craton. Those same currents likely sheared away pieces of keel until the deep root was gone, replacing once rigid Cratonic mantle with hotter, weaker material. Evidence for this dismantling is found in two very different classes of rocks. Older volcanic xenoliths from before the root collapse contain minerals depleted in melt-producing elements, the hallmark of classic Cratonic mantle. Younger samples, however, erupted with much denser compositions typical of ordinary upper mantle. That turnover means the ancient keel had already disappeared by the time those magmas rose. Seismic imaging taken in more recent decades has reinforced the picture. The lithosphere beneath eastern North China today is less than half as thick as a Craton would require, with its base resting around 80 kilometers deep where once it extended more than 200. Combined, these records draw one of the most convincing portraits we have of root destruction in action. The consequences were profound. Without the buoyancy of its keel, the crust of eastern North China became weaker and more mobile. Faulting and extension reshaped its landscapes. Once quiet interiors became seismically active, and new volcanic fields opened routes for magma to reach the surface. Meanwhile, mineral-rich fluids released during the breakdown of the root supplied gold and other metals that we still mine today. The collapse removed stability, but also created resources, a reminder that Cratine death changes not just deep Earth structure, but the very surface on which societies later emerge. This episode forced geologists to rethink what a Cratine actually means. It is not the continent itself, but the buried skeleton that grants stability to the crust above. North China made it clear that removing that skeleton does not erase the continent. Instead, it changes the way that continent behaves. What was once a stable core became a zone of active tectonics, a place where volcanism proliferated and mineral wealth multiplied. In that light, Craton collapse is not only a destructive process, but a transformative one, reshaping entire regions for tens of millions of years after the root is gone. The broader implication was unavoidable. If North China's root could be stripped away, then no Craton is beyond risk. Their reputation as eternal is a matter of perspective. A billion years of survival is staggering to us, but not permanence to Earth. By linking xenolith chemistry, magmatism, mineral deposits, and seismic profiles, researchers built a complete case that Craton keels are not geological immortals, but features with lifespans and endpoints. That realization shifted the search elsewhere. If it happened here, could it also be happening beneath other continents today? Answering that question required a new kind of evidence. Geologists need to catch a Craton in the act of losing its root, not just reconstruct its disappearance millions of years later. Observing directly at depths of 200 kilometers was and remains impossible. No drill could reach that far. No borehole can withstand those pressures and temperatures. The challenge was finding a way to see into the mantle using signals that naturally cross it. Only then could scientists hope to compare a past case like North China with a present-day one still underway. And so the focus turned to Earth's natural probes, earthquakes, imaging the unimaginable. Studying what happens hundreds of kilometers underground is almost impossible with direct tools. No drill could ever reach so deep, and even if it could, material would collapse under crushing pressure and heat. Instead, researchers turned to waves moving through Earth itself. When an earthquake occurs, vibrations radiate outward. Those waves speed up through colder, rigid rock and slow down in hotter or weaker zones. By recording thousands of arrivals at surface stations, geophysicists can reconstruct a picture of the structures that shape the waves. It's like using ultrasound, sound waves returning as images, except on a planetary scale where the signals come not from a machine but from Earth's own tremors. The approach is called seismic tomography. What makes the latest effort remarkable is the precision of its methods. Instead of relying only on timing differences from one point to another, the team applied full waveform seismic tomography, which models the entire shape of the passing signal. Combined with a massive dataset, roughly 206 earthquakes recorded at about 6,000 seismic stations across North America, this strategy produced the clearest three-dimensional images of the deep lithosphere yet. Those maps trace structures stretching far into the mantle, well past the shallow crust and underlying keel, and in many cases extending downward toward the mantle transition zone, roughly 400 to 600 kilometers deep. That level of detail gave researchers their first direct look at how North America's Craton is behaving below the surface. The expectation was straightforward. A thick, solid keel should show up as a continuous block of unusually fast seismic velocities, the unmistakable footprint of cold, dense mantle lithosphere. Instead, the imaging revealed something very different. Parts of that keel appeared broken apart, rather than one uniform sheet. The tomography displayed Driplike blobs of high-velocity rock, detaching from the underside of the Craton and sagging down toward the transition zone. For decades, geologists suspected this process might be possible. They debated whether mantle flow could. slowly erode even the most chemically hardened roots, but until now their evidence came only from indirect clues like xenolith chemistry or volcanic eruptions. Here, for the first time, the process was captured mid-act. These detached shapes are not illusions or artifacts. Their seismic velocities confirm they are colder than the material they sink into. Imagine exactly what blocks of Cratonic root would look like if they were peeling away. The scale of motion is almost beyond human comprehension. The drips move at geologic pace, shifting millimeters to centimeters over a year, so to us they appear frozen in place. Yet on Earth's timescale, this is rapid. Over millions of years, entire portions of foundation can be displaced. What we see in the maps is essentially a time-still frame of a continent losing its anchor, instead of a static confirmation that roots can disappear. This is the first visual evidence of one actively unraveling. The work also highlights why tomography is such a powerful tool. Each earthquake wave takes a unique route, cutting across Earth's interior from a different angle. One path alone is like a single shadow, offering almost no depth. But stack thousands of such paths. Waves crossing, bending, and scattering, and patterns emerge with enough definition to recover real structures. Thanks to computational advances, those thousands of records now combine into high-resolution models capable of distinguishing features less than 100 kilometers across. Without so many seismic stations operating in unison across a continent, the drips of North America's Craton would stay hidden. Equally important is that tomography makes these findings testable over time. Because the method relies on natural earthquakes, each new event can add a frame to the record. By returning to regions with updated data and recomputing the models, researchers can watch for changes in the lithosphere's anatomy. The potential to track long-term disintegration of continental roots means geologists may soon move from speculative cases to trend lines, noting how fast the keel fragments and whether pieces settle in the transition zone or keep sinking deeper into the lower mantle. Until recently, the destruction of Cratons was explained only in hindsight. Rocks at the surface carry whispers of vanished roots. Now, seismic tomography has shifted that picture from reconstruction to observation. Instead of only inferring that North China's root disappeared millions of years ago, we see North America's root deforming and dripping in the present. That revelation marks a turning point. For the first time, continental loss is observable as it unfolds, not only as an afterthought preserved in magma and minerals. Still, identifying the drips only raised a larger question. Why here? Why would one of Earth's great continental interiors, long thought to be among the most stable regions, suddenly begin shedding its foundation? The tomography maps provided the first suggestion. Alongside the sagging root fragments, they revealed an even larger anomaly running deep beneath the continent. And that is when the team began looking for a cause. What they uncovered pointed to something vast, still hidden below North America, a structure that outlived the ocean it once belonged to and continues to shape mantle circulation today. The phantom plate beneath our feet. What tomography uncovered beneath North America was not only the slow dripping of its cratonic root, but also the preserved remains of something far older, a vast oceanic plate that no longer exists at the surface. This was the Farallon plate, once spread across an ocean west of the continent. For millions of years it pushed eastward, diving under North America at the margin and sinking into the mantle. Surface rocks show little sign of it today. The ocean closed and the plate boundary vanished, but seismology paints a different picture. Clear fragments of the Farallon still lie deep within the Earth, lodged hundreds of kilometers down in the mantle transition zone and even parts of the lower mantle. It is a relic of an ancient ocean plate, now parked in the mantle and still tugging at the continent above. The Farallon was enormous, large enough to reshape half a continent during its descent. Its subduction fueled the rise of the Rocky Mountains and drove dramatic volcanic activity across western North America. Oceanic crust was scraped off and recycled into Earth's interior as the plate slid downward, while immense heat and pressure altered the geology above. Though the plate's surface expression has long disappeared, imaging shows that much of its body remains preserved deep within the planet, folded and warped but still intact. Instead of decaying quickly into the surrounding mantle, parts of it stalled in place, piling up and disrupting the flows of material nearby. Most subducted plates gradually warm and blend back into their surroundings after sinking. Over tens of millions of years, they lose their coherence, leaving the mantle more or less homogeneous again. The Farallon has not followed that usual pattern. Seismic studies reveal fragments lodged in the Mantle transition zone roughly 400 to 600 kilometers down, and others extending deeper into the lower mantle. Its position and immense size have made it behave less like a fleeting slab and more like a permanent feature, shaping mantle circulation itself. That unusual persistence matters because the very presence of such a slab changes how mantle currents move. Hot plumes trying to rise, or convection trying to circulate horizontally are diverted or blocked by its bulk. For the continent overhead, that means its stabilizing keel no longer floats in a calm environment, but instead is battered and stretched by redirected currents. Computer simulations of mantle circulation confirm this link. When researchers built models without the Farallon plate, the convection beneath North America flowed relatively smoothly, with the Cratonic root above remaining thick and buoyant over billions of years. But when the Farallon was included as a massive stalled slab, the scenario changed. Mantle flow became uneven, sweeping forcefully against the Craton's base. Infiltrating pockets of material further weakened the route. In every model case, dripping of the Cratonic keel occurred once the Farallon fragment was present. Remove the slab and the dripping disappears. Keep it in place and the root destabilizes. That direct comparison made the mechanism plain. The relic plate is not just a bystander, but the active driver of the ongoing disintegration. The presence of this slab explains why North America's Craton, long considered among the sturdiest on Earth, now shows evidence of breaking down. The Craton itself retains the chemical and structural traits that normally protect it from erosion. It is depleted, dense, and rigid. Yet combined with the massive forces of mantle circulation distorted by the Farallon, these traits cannot guarantee security. The slab continues to interfere with patterns of heat and flow, dragging, shearing, and weakening the base of the continental root. Rather than arising from the Craton itself, the instability originates externally as a consequence of plate tectonic history, stretching back more than 100 million years. This realization reframes how geologists understand continents. Subduction does not erase a plate completely. Parts of it may sink to depths beyond direct reach, but still remain intact for tens of millions of years. These buried remnants act like boulders in a river, reshaping everything around them. The Farallon is the clearest case study. Its preserved mass redirects mantle flow, releases fluids as it dehydrates, and introduces mechanical stresses in all directions. What tomography and modeling now show is that even the most resilient continent can be destabilized by inheriting such a neighbor underground. It also clarifies a puzzle that long bothered researchers. Earlier explanations for Craton destruction centered on local heating, stretching forces from above, or general mantle erosion. But none of those alone could fully explain the scale of root loss observed in places like North China, or the active dripping now unfolding beneath North America. Once the role of the Farallon was factored in, the patterns made sense. The slab does not cause dripping by itself, but by warping mantle flow and injecting fluids into once dry root, it sets the stage for portions of lithosphere to detach and sink. The models demonstrate that without its presence, stability would likely endure for far longer. With it, the root cannot remain intact indefinitely. From a human perspective, it's important to stress the timescale of these changes. The dripping we observe will play out over millions of years. People living on the continent will not notice sudden collapses or immediate hazards linked to this deep mantle activity. The significance here lies in understanding Earth's long-term evolution, not in predicting disasters within our lifetimes. Geological processes rarely move at speeds relevant to human society, and in this case, the researchers emphasize that once the slab fragments eventually sink deeper into the mantle, the destabilizing forces may ease. In other words, this is a long-term natural cycle, not an urgent threat. Still, the implications stretch beyond North America. If the fate of a Craton can hinge on the remnants of an ancient plate buried beneath it, then other so-called stable continents may also carry hidden vulnerabilities. Every continent has a tectonic history, written not only in surface rocks, but also in the slabs swallowed long ago and still preserved at depth. In North America's case, the Farallon provides a unique window into how past plate motions continue to dictate the present structure of the continent. Millions of years after the ocean had birthed, it has vanished. By combining seismic imaging with geodynamic models, scientists have built a coherent mechanism linking a buried plate to the ongoing dismantling of continental keel. It is a rare moment where evidence from multiple approaches converges on the same answer. The dripping of North America's Craton is not random or inevitable. It is a predictable consequence of a large, dense slab interfering with mantle circulation, dragging a continent into instability. That leaves us with an essential question. If mantle flow distorted by an ancient plate can destabilize the very base of a continent, what else contributes to those roots actually breaking apart and turning into drips? The tomography showed the connection, and the modeling confirmed the mechanical trigger. But understanding why pieces of Craton truly melt, weaken, and fall requires looking one step further into what happens when subducted plates deliver their hidden cargo to the mantle around them, the cocktail of destruction. The key to understanding why a Cratonic root starts to come apart lies in what geologists sometimes call the cocktail of destruction. On its own, the root is cold, stiff, and chemically depleted, traits that make it unusually resistant compared to the surrounding mantle. But once a subducted oceanic plate moves beneath it, the environment changes. Oceanic crust carries minerals packed with water, carbonates, and other volatiles. As the plate sinks into higher pressure and temperature, those minerals break down and release fluids into the mantle. When these fluids seep into the base of a Cratonic keel, they act like a solvent, lowering its melting point, softening its once rigid structure, and reintroducing elements that undo its buoyancy. Suddenly, a foundation that was designed to float becomes denser and easier to deform. At the same time, mantle circulation reshapes how forces act on the root. Subducted slabs do not simply slide down out of view. They reshape the flows around them. The Farallon plate, preserved beneath North America, redirects mantle currents in complex ways. Those currents bend and shear against the Craton's base, applying steady stress over immense spans of time. With fluids already weakened in the material, those flows no longer glance past harmlessly. They latch onto softened patches and pull them apart. Piece by piece, sections of the keel detach, separating into dense, irregular chunks that gravity draws downward. The outcome is not a clean fracture, but a slow peeling process, where each blob of lithosphere sags and sinks into the deeper mantle. Seismic tomography confirms the nature of these detached bodies. The images show anomalies that are modestly cooler by about 60 degrees Celsius than surround the mantle, which matches expectations for displaced continental material. Their composition appears enriched in Cratonic signatures, containing 20 to 50% more continental lithosphere than the mantle around them. These are not random mantle plumes. They are unmistakably pieces of the Craton itself stripped from below. Models estimate that in affected regions, this thinning has already removed between 20 and 60 kilometers of lithosphere. That may not sound dramatic compared to the root's overall thickness, but it represents a substantial loss of stabilizing mass over geological time. The combined sequence is simple. Fluids weaken, mantle flow pulls, and detached sections drip away. Neither factor on its own is sufficient. Fluids alone soften but do not detach, while flow alone pushes but cannot overcome the keel's rigidity. Together, they create the instability we now recognize in tomography. Each drip represents a cycle repeated over millions of years, steadily eroding what once seemed immovable. What makes this process remarkable is that it escapes notice at the surface. Standing on the continent above, nothing appears to change. The crust remains solid, landscapes continue their normal pace of uplift and erosion, and life goes on without disruption. Yet far below, volumes of rock comparable to entire mountain ranges quietly peel away and vanish into Earth's deeper layers. This is erosion running in reverse, not weather or rivers wearing down from above, but mantle circulation hollowing from below. And that raises the pressing question. If the root beneath North America is actively thinning, what consequences will arise for the continent sitting on top of it? Why it matters for North America. There is no danger that North America will suddenly lose stability at the surface. The changes happening deep underfoot operate over geological timescales, millions to tens of millions of years, far outside human experience. For life above, the crust remains firm and stable. But over Earth's long rhythms, the gradual thinning of the Cratonic root alters how the continent behaves. Losing that deep keel means the surface becomes more exposed to mantle influence, and that exposure has clear consequences. Volcanism can appear in unexpected places. Faults may shift into new activity. Basins can form as the land sinks unevenly. Mantle heat reshapes crustal strength. And mineral-rich fluids may concentrate resources in entirely new zones. These effects are not speculative guesses, they have precedent. The best-known example comes from the North China Craton. Their deep root loss coincided with widespread volcanism and the formation of major gold deposits. What seemed like a stable ancient continental interior transformed into an active geological province. North America now sits at the beginning of a comparable process. Its tomography images show dripping roots, and that signals not collapse at human pace, but reconfiguration of the interior landscape over deep time. One of the most recognizable outcomes of root thinning is a change in volcanic activity. Today, North America's key volcanic centers, the Cascades, the Yellowstone hotspot, and chains of extinct fields inland are relatively well mapped. They trace where magma can rise through weak crust, but when sections of the keel are removed, new avenues open. Magma that was once trapped by the base of a thick cold shield may instead rise freely, igniting eruptions across previously quiet ground. Geological maps built on past knowledge will not predict these fresh fields because the controlling factors beneath the crust are no longer the same. Over millions of years, volcanic zones can shift inward, and new eruptive centers may appear where they are least expected. Root loss also redistributes stress above. A strong keel spreads tectonic forces broadly, helping the crust resist cracking. Without it, strain focuses more locally. Over long spans, this concentration of stress encourages faulting and deformation. What had been a stable continental interior can gradually take on the behavior of a tectonic margin. Earthquakes occurring across zones once considered passive, landscapes flexing upward or downward, and entire basins tilting. The Rocky Mountains, the Great Plains, even the Mississippi Valley exist within the zone of influence. While nothing like surface collapse lies ahead, the stresses that accumulate could gradually reshape the continent's geometry. Subsidence and basin formation follow naturally from those changes. Cratons are buoyant because their roots are light compared with the surrounding mantle. Strip away that buoyancy, and the continent as a whole responds by sinking. This process is slow, but it doesn't happen evenly. Some regions drop more than others, generating lowlands that fill with sediment. Over time, these sinking basins create new landscapes, fresh river systems, and altered coastlines. In North America's deep future, parts of today's high ground could relax into depressions, while nearby terrain rises or tilts to balance the shifting weight. Such gradual but profound changes leave an imprint that persists for tens of millions of years. The redistribution of heat is another factor geologists emphasize. Thick roots act as lids that shield the crust from warm, mobile mantle. Without that cover, replaced mantle is harder and more chemically fertile. That means previously rigid crust begins to soften, thin, and potentially weaken into zones of partial melt. In the long run, this transition undermines the interior's ability to act like an immovable block. A continent once defined as a geologic stronghold may transform into one more prone to bending, stretching, and responding to mantle convection currents. Finally, mineral resources bear the signature of root collapse. Cratons are already known for producing diamonds, nickel, iron, and gold because of the unique chemistry at their bases. When roots degrade, the fluids released carry those elements into higher crustal zones. In the North China case, this process generated extraordinary mineralization, belts of gold linked with the same magmatism that marked the Keels destruction. For North America, such enrichment would take millions of years, but the principle remains. Areas now seen as stable and unremarkable could one day contain concentrated reserves created by the breakdown of the root below. Taken together, these consequences redefine what geologists mean when they describe a continent as stable. North America's interior appears steady from our vantage point, but tomography shows the foundation already changing. At the surface, nothing feels different, yet the blueprint beneath is rewritten slowly, one drip at a time. Volcanic centers may migrate across the interior, earthquake patterns may shift, sedimentary basins may deepen, mantle heat may erode the crust rigidity, and mineral belts may concentrate in unexpected zones. A landmass long portrayed as immovable reveals itself as dynamic once time is measured not in centuries but in millions of years. This perspective also reshapes how geology is taught and imagined. For decades, classrooms described North America's heartland as one of the most inert continental cores anywhere on Earth. Active lives on the margins. Students learn while passive interiors sleep unchanged. Seismic imaging has reversed that story. Interiors, too, can leap, deform, and evolve. The categories of margin versus core are not fixed. They adjust as mantle processes reorganize. What feels unmoving to human societies is only paused at a larger scale. A simple image captures the shift. Imagine a raft floating on water. With its keel attached, the raft rides high, immune to small shifts below. Remove that keel, and the raft persists, but it lowers, tips, and becomes more sensitive to current and turbulence. The continent above behaves the same way. The crust remains, but without its thick stabilizer, it reacts more strongly to the mantle system beneath. That change does not erase the raft, it redefines how it moves. North America, once thought endless in its rigidity, is adopting a more flexible relationship with the processes below. The key idea is not abrupt change, but slow transformation. The crust of North America is not vanishing. Its future, however, will not perfectly resemble its past. The outlines of mountains, valleys, rivers, and resource belts are being redrafted beneath the surface, laid down now as subtle variations captured in seismic waves. Those patterns are more than abstractions. They foreshadow the structure the continent will carry millions of years ahead. And one dimension of this transformation is especially striking. Root collapse does not just weaken and destabilize. The same process alters chemistry in ways that create new concentrations of Earth's most valuable resources. This side of the story shifts attention from erosion and sagging ground to the possibility of wealth forged far beneath. What geologists are learning is that the destruction of a Craton can also be the setup for a geological factory, one that works on scales of heat, pressure, and time unimaginable to us. The diamond factory beneath us. Cratons are not only the structural core of continents, they are also the planet's great mineral storehouses. Their deep coal roots create chemical environments that stabilize unusual reactions in the mantle. Over immense spans of time, these reactions trap precious elements and preserve the extreme conditions needed for crystals like diamonds to exist. That is why so many of the world's diamonds, much of its platinum group elements, and significant portions of gold are associated with Cratonic regions. The same keel that holds a continent steady also shapes the pathways for magmas, especially Kimberlite eruptions, that bring diamonds and other deep materials rapidly to the surface. In short, the invisible foundation beneath our feet has always doubled as a geological factory of rare resources. When those roots begin to erode, the story changes. A thinning keel does not simply shrink in silence, it alters the chemistry and flow of the mantle around it. Normally, a thick curtain insulates its underside, sealing it away from volatile rich mantle material. But when pieces drip off, that insulation is breached. Water and carbon from old seafloor slabs rise into new gaps, lowering melting points and producing small batches of magma with unusual compositions. These magmas are particularly efficient carriers of metals and volatiles, moving gold, nickel, and diamonds up into the crust. Over geologic time, this shift in plumbing can redirect the concentration of valuable deposits. Root loss, therefore, is not just structural. It changes where a continent's resources gather. The clearest example comes from the North China Craton. Geological evidence shows its keel collapsed during the Mesozoic, roughly 100 to 200 million years ago. At that time, mantle magmas infiltrated the thinning lithosphere, releasing volatile rich fluids that deposited vast amounts of gold near the surface. Today, those belts remain among the richest gold provinces in Asia. This sequence, root stripping, fluid release, then mineralization, provides a direct precedent for what happens when a Craton transforms chemically, not just physically. The timing matters. Enrichment unfolded over tens of millions of years, not in any moment we could observe. Yet once complete, it permanently altered the resource map of the region. North America's tomography images indicate a similar process may already be underway on a timescale far longer than human memory. As pieces of its Cratonic root sink, hotter and wetter mantle rises to replace them. That material contains not just heat but also the chemical ingredients delivered into the mantle by ancient subduction. Over repeated cycles, fluids infiltrate cracks in the lithosphere, sometimes dissolving host rocks, sometimes crystallizing new minerals. In long view, this could mean entire belts of gold, nickel, platinum group elements, and potentially new diamond deposits forming inland in areas not considered mineral provinces today. The transformation is subtle and imperceptible now, but it is already programmed into the deep plumbing beneath the continent. Diamonds themselves highlight the paradox. They can only form at extreme pressures and temperatures found in the bases of Cratons. Stability allows them to survive for billions of years, trapped far below ground. But those same thick roots prevent them from ever being released. When the root is destabilized, the conditions for diamond growth diminish, yet another opportunity opens. Fast Kimberlite magmas exploit weakened zones to erupt. These explosions act like elevators, pulling ancient diamond crystals to the surface before they can dissolve. The erosion of a root, therefore, does not create new diamonds directly, but enables a mechanism to retrieve ones already made and hidden away for geologic ages. Other metals respond to the same changes. A strong root isolates them in a mantle beyond reach of surface processes. A weakened one exposes them to hydrothermal circulation, where flowing fluids concentrate metals into veins and clusters. Over millions of years, those become the ores mined at the surface. In this way, the collapse of a keel converts a locked vault into an active delivery system. The enrichment is not sudden. It is gradual, cumulative, and tied to the deep circulation of fluids and magma that only become available when the keel fails. For North America, these processes mean the future geology of the continent is not simply about strain, faults, or volcanism. It also involves the rearrangement of where resources are likely to form. Canada's existing diamond fields are already linked to deep Cratonic roots. If tomography maps are correct, the roots now thinning could expose fresh mantle pathways that will, in millions of years, deliver entirely new deposits. In the distant future, the areas we consider quiet interior landscapes may be mineral provinces shaped directly by the weakening of the Craton below. The contradiction at the heart of this story is clear. Cratons defend continents from tectonic disruption, yet their destruction releases the chemistry that makes rich mineral provinces possible. Both outcomes matter to societies that depend on geological resources. One grants stable ground for cities, the other establishes the ores and fuels for those cities to thrive. When geophysicists look at tomography and see descending blobs of lithosphere, they recognize a weakening root. When economic geologists look at the same images, they see the first steps in a process that eventually concentrates metals to mine. Root loss is, in its simplest terms, a plumbing change, one that controls where heat, fluids, and minerals move inside a continent. The long view is therefore less about collapse than reorganization. The weakened root beneath North America points not only to structural rearrangement, but also to a slow beginning of resource redistribution. The chemistry of ore bodies, the presence of diamonds, or the rise of new gold belts in deep time all stem from the same process, the transfer of elements to a root that is no longer fully intact. Human lifetimes will never capture these changes directly, but for Earth science they are a defining signal of how deep mantle processes shape the surface economy of continents. Saying this way, the Craton under North America is not simply fading. It is quietly reshaping the distribution of resources that will define the continent long after our present era. Its slow failure prepares the ground for mineral provinces that may one day rival those produced in places like North China. The fingerprint of those changes is already present in seismic images. What appears to geophysicists as small anomalies are also the seeds of ores, crystals, and deposits that will one day surface. Hidden beneath all of this remains a subtle theme. The physics of continental roots control not only whether continents stand firm, but also how they ride atop the shifting mantle itself. And the same changes that supply a new wave of resources also alter how entire land masses respond to the fluid earth beneath them. Continents that float. Continents often feel like unchanging platforms, but in reality they float. This balance is governed by the principle of isostasy, the same effect that makes icebergs appear partly above the ocean while most of their bulk lies hidden below. Solid land behaves the same way, resting on the flowing mantle. Beneath. Cratonic roots are crucial to this equilibrium. They are thick, cool, and less dense than surrounding mantle, so they act like buoyant supports that keep continents riding high. It is why much of central North America sits elevated even without young mountains to prop it up. But when those roots thin or drip away into the mantle, the balance shifts. Over millions of years, the crust above adjusts downward, forming broad basins or even shallow inland seas. Geological records preserve these episodes in sedimentary layers left behind when seas spread inland, showing that buoyancy loss reshaped landscapes long before humans ever set foot on them. This floating balance also explains why sedimentary basins repeatedly appear and vanish within cratonic interiors. Each basin represents not erosion from above, but the slow sinking of crust responding to quiet adjustments at depth. The fills of sandstones, shales, and limestones that geologists study today are, in many cases, archives of those buoyancy shifts. Cratonic basins may not look dramatic, but they tell the story of continents behaving like rafts, stable yet subtly rising and falling depending on the state of their roots. What stands out is how far-reaching such adjustments can be. A slight reduction of density or thickness at depth results over geological time in surface changes of hundreds of meters in elevation. Coastlines migrate, rivers reroute, ecosystems adjust, and sedimentary layers accumulate across continental interiors. None of this happens quickly. From our perspective, land feels firm. But seen from Earth's timescale, continents are always negotiating their buoyancy. For North America, the tomography images showing dripping cratonic roots are more than evidence of mantle interaction. They are signals of long-term elevation changes still to come. As buoyant support weakens, some areas of the interior will sag, others may respond with uplift, and new basins will quietly prepare to collect sediments. The motion is imperceptible across a lifetime, but unmistakable when traced across the rock record. This understanding reframes how we read ancient landscapes. What appears to be the product of surface weathering is often rooted in adjustments too deep to see. Sediment stacked in wide basins, inland seas advancing and retreating, and differences in crustal thickness across a continent all reflect the slow search for balance in a floating system. The continent persists, but never in quite the same form for long, and that raises an almost paradoxical perspective. The ground beneath us feels solid, yet its height and form are tied to processes invisible and glacially slow. To appreciate those changes requires stepping outside human scales and placing them on Earth's clock, where even a million years counts as little more than a flicker. The strange clock of geological time. The deeper lesson behind root laws comes from recognizing how Earth keeps its own time. Geologists measure this using the strange clock of geological time, a clock where a million years is barely noticeable and a billion years is a reasonable unit of comparison. Within that framework, Cratons represent some of the most enduring structures the planet has produced. Parts of North America's crate interior have remained stable for over 1.3 billion years. Against that backdrop, the timetable for thinning, measured in pulses of just tens of millions of years, looks startlingly fast. This is where perspective matters. To humans, tens of millions of years are essentially forever. But put next to the multi-billion-year lifespan of a Craton, those intervals feel abrupt, like watching something ancient suddenly develop cracks in real time. The North China Craton demonstrates this. It existed for billions of years before losing its keel within a span geologists count as brief, just a few tens of millions. What Earth shows us is that processes invisible to us are, in its scale, rapid events that can redirect volcanic fields, concentrate mineral belts, and destabilize entire regions of crust. Seismic tomography gives this abstract pace a physical measure. Detached root fragments tens of kilometers wide are visible in the mantle, each representing material that tore away over just a few million years. When placed on a clock measured in billions, these are not slow leaks, they are rapid discharges. It is the equivalent of watching the wall crumble brick by brick, not over centuries, but across a few short decades, if measured in human proportion. The paradox is what makes the imagery so powerful, at once both imperceptibly slow and geologically fast. To see this duality, one only needs to consider the scale of movement. A drifting root fragment may sink just centimeters per year. That distance is nothing compared to the motion of rivers, glaciers, or even a spreading tree root above ground. Yet stretch that across 1 million or 10 million years, and it becomes a mass hundreds of kilometers across. Shifted deep into the mantle. Small rates multiplied by immense time add up to the restructuring of a continent's foundation. The land above appears unchanged, but inside Earth's own measure, it is a continuous transformation. This is what researchers mean when they speak of Craton decay as fast. They are not thinking in the frame of our history, which counts back tens of thousands of years at most. They are measuring against the lifespan of a Craton itself, a structure that can stabilize for more than 1 billion years but lose its keel in less than 100 million is, in planetary terms, collapsing quickly. That speed aligns with the pace of other continental processes. Plate collisions, rifting, and the cycles of supercontinent formation and breakup all unfold on similar timescales. Cratonic roots, once thought permanent, prove instead to be part of the same rhythm. And in that rhythm lies the real impact. While this drip-by-drip erosion has no effect within a single human life, across the longer beats of Earth's history, it reshapes what continents are and how they behave. By the time one supercontinent dissolves and the next begins to assemble, entire sections of keel may have vanished underneath. A stable continental heartland becomes an active zone. Resource belts appear where mines once seemed unthinkable. In that sense, the strange clock of geology does not mark years or centuries, but milestones of planet-scale restructuring. The research emphasizes this dual scale because it reframes what stability means. For us, the continents beneath our feet might as well be eternal. They do not bend in ways we can see, and their surfaces change slowly by weather and rivers. For Earth, however, the continent is already shifting. The tomography snapshots are evidence of transitions that, while invisible now, will accumulate into lasting change. Hundreds of meters of surface elevation may rise or fall across interiors. New magmatic provinces may emerge, and once quiet regions could one day open into faults and basins. Stability in the human sense is really just pause. In Earth's sense, it is motion. Even the numbers themselves highlight this point. A root fragment tens of kilometers thick may separate from the Craton every few million years. Repeat that motion across 100 million years, less than the lifespan of a group like the dinosaurs, and the total loss rivals the depth of an entire keel. These scales overlap neatly. While ecosystems rise and vanish, so do sections of lithosphere that once supported everything above. That comparison reminds us that continents are no more permanent than the species that live on them. Their endurance feels eternal because our perspective is so narrow, but Earth's clock reveals them constantly in revision. This is why the North American case matters beyond academic curiosity. Parts of its Craton have persisted since deep time, as stable for more than 1 billion years as any region on the planet, but tomography now suggests it could begin losing large portions of that stability in spans tens of millions long, shorter than the gap between supercontinent cycles. What we're seeing is not a continent collapsing before our eyes, but one entering the next chapter of its long history. The discovery redraws the boundary between permanence and fragility, showing how quickly even the strongest foundations can change when set against planet-scale time. And so, the strange clock of geology tells us something essential. What appears fixed to humans is already transient to Earth. No city, species, or even civilization will ever notice the dripping of a Craton in real time. But in the span of the next geological epoch, it is enough to redirect magma, remake landscapes, and rewire our continent's resources. The evidence in North America is simply one signal of this deeper truth. Continental interiors, too, are temporary arrangements in a dynamic planet, which raises a larger question. If North America shows these changes today, is it unique, or do other continents also carry the seeds of the same transformation? Could it happen elsewhere? Across the planet, other Cratons show evidence that their ancient roots are not immune to thinning or even removal. The most widely studied example is the North China Craton, where research demonstrates that a keel once more than 200 kilometers thick was stripped away during the Mesozoic. Volcanic xenoliths confirm the transition from depleted Cratonic mantle to ordinary upper mantle, and the timing aligns with widespread volcanism and the emergence of one of the richest gold provinces in Asia. Here, scientists can see the entire arc of collapse, how a route that stabilized for billions of years was lost in just a short geological interval. In western North America, geophysical imaging reveals modifications that suggest Cratonic lithosphere has also been thinned by subduction-related processes. Parts of the once continuous keel beneath regions like the Sierra Nevada and Basin and Range now show reduced thickness and signs of metasomatism, where slab-derived fluids infiltrated the lithosphere and weakened it. These patterns resemble what tomography displays under the central Craton today, though the western examples represent earlier stages of disruption rather than wholesale detachment. Evidence drawn from both xenolith chemistry and seismic velocity profiles reinforces the interpretation that sections of North America's root have already been replaced or altered by hotter mantle over time. Southern Africa provides another important case. The Craton, celebrated for hosting some of the world's deepest diamond mines, is not entirely untouched depth. Tomography and magnetotelluric surveys suggest the base of the root has zones that are thinner and chemically modified compared with its interior. The evidence points to metasomatic alterations, mantle fluids changing the composition of Cratonic lithosphere, and possibly localized removal at boundary zones. Although the cop ball retains a thick keel in most areas, its margins demonstrate that even the strongest Archean Cratons can be altered by surrounding mantle processes. India offers a further example. The Darwa Craton forms much of the southern Indian Shield and remains extremely ancient, but geophysical models show that beneath portions of the subcontinent, the lithospheric roots are notably thinner than typical global averages. India's ongoing collision with Eurasia introduces complex stresses and mantle flow that likely contribute to slow weakening. While the southern Craton still appears stable, the tectonic context, marked by subduction zones to the east and the immense convergence in the north, makes it a critical region for observing how large-scale forces influence cratonic integrity. Taken together, these cases illustrate that North America is not an outlier. Multiple well-documented examples demonstrate that cratonic roots can be thinned, modified, or destroyed under particular conditions. Each continent provides its own natural experiment. Subduction is a key driver in some regions, as with North China and Western North America. Mantle plumes in an anomalously hot mantle environment appear influential in Africa. In India, continent-to-continent collision provides a different pathway toward destabilization. No single mechanism explains all cases. Instead, each instance reveals how diverse mantle processes can converge on the same outcome. Erosion is the Craton's ancient keel. This perspective shifts the question from whether root loss can happen to where and how it occurs. In North China, the evidence of mineralization and magmatism marks the aftermath. In Western North America, geophysical data catch an earlier stage of thinning. In southern Africa, subtle signals of metasomatism record ongoing modification. In India, tectonic stresses may set up vulnerability for the future. Each gives researchers a different point along the timeline of Craton evolution, from early weakening to complete collapse. The importance of compiling these examples lies not only in mapping past changes, but in building predictive understanding. By comparing regions, scientists can test hypotheses about which factors matter most. Does proximity to subduction zones accelerate destruction? Do mantle plumes destabilize even interiors far from plate boundaries? How does metasomatic alteration precondition keels for later detachment? Each story, China, North America, Africa, India, helps to constrain those questions, providing real-world laboratories rather than theoretical models alone. Viewed in this context, the North American evidence adds another essential piece. The tomography maps do not show only indirect traces or aftermath. They capture the process unfolding in real time. That live observation strengthens the case for how fluids, mantle currents, and mechanical stress interact. When combined with the outcomes preserved elsewhere, such as mineral belts or thin keels, a clearer model comes into focus. Craton stability is not permanent, but conditional, dependent on the long interplay between lithosphere and mantle environment. The broader point is not that every craton is destined to collapse soon or identically. Many cratons still retain their keels largely intact after billions of years and may continue to do so for vast spans of future time. But the accumulating evidence from different continents demonstrates that root loss is an established part of Earth's geological cycle. It happens under different triggers, at different rates, and with varying consequences, but it is not an anomaly confined to one setting. North America's slow-dripping roots simply extends the sequence of cases already documented. What these comparisons ultimately provide is a stronger foundation for modeling Earth's future. Each example, whether a complete collapse, active thinning, or subtle chemical change, becomes one data point in reconstructing how continents evolve. Together, they show that the architecture of continents is dynamic, shifting under forces that vary across the globe. By assembling these cases, geologists can refine their projections, which interiors are most secure, which are vulnerable, and how the interplay of subduction, mantle plumes, and tectonic stress reshapes Earth's surface over time. The conclusion from this comparative view is straightforward. North America is not unique, and Cretan erosion is not confined to one place. Documented cases around the world confirm that thinning and removal of continental roots have already occurred and are still occurring today. These are not theoretical possibilities, but observed realities. And recognizing that they happen in diverse contexts makes the evidence from North America all the more compelling. It is one chapter in a much broader history of continents adapting, deforming, and reorganizing under the motions of the mantle. Seen this way, the question is not whether Cratons can decay, but how long the process takes and what surface consequences follow. With every new seismic survey, xenolith analysis, or geodynamic model, scientists add to the timeline of how Earth recycles its most ancient structures. Comparing regions sharpens rather than blurs the picture. The fading of North America's keel fits into a global framework, but the evidence there, direct, high-resolution, and ongoing, makes it uniquely valuable for testing our understanding against present reality. This shared context also points back to why the subject matters at all. If Cratonic roots carry within them the conditions for future volcanism, mineral belts, basins, and tectonic shifts, then their stability defines how continents provide resources and landscapes. The comparative record shows that change is the rule, not the exception. Whether the trigger is a descending slab, a rising plume, or chemical weakening from fluids, the result is ultimately the same. Once rigid keels that protected continents for billions of years can end and fail. Studying these patterns across continents does more than reconstruct Earth's past. It sets the stage for understanding the transformations still to come. Each observed case adds weight to the realization that continents are not permanent anchors. They shift, weaken, and respond over time to the mantle beneath them. The record from China, Africa, India, and beyond underscores this reality, leaving North America's case not as an anomaly but as the most detailed example yet of an ongoing cycle. And that perspective brings us back to the ground under our feet. For all its apparent solidity, the base of our continent is engaged in the same cycle as others, slowly altered, sometimes thin, sometimes lost, always in motion on Earth's timeline. It is the setting for what happens next when we turn back to the continent we inhabit and consider what its disappearing root tells us about the land we trust to stay still. Seismic imaging has now made one thing undeniable. North America's ancient root is slowly dripping into the mantle. The process unfolds over millions of years, invisible to us but real on the planet's scale. There's no imminent collapse. The land we live on remains secure. But in geologic terms, the foundation is already changing. The takeaway is simple. Even Earth's most durable structures have lifespans. For the first time, we can watch those deep foundations shift while continents are still in place. So here's a question for you. Where do you live? And had you ever imagined the ground beneath you could be this dynamic? And one last thought. If Cratons can drip away, what will the map of Earth look like 100 million years from now?